Welcome to Integrated Math 3. On this episode, Stevenson will demonstrate Let's look at the transformational form of an exponential function. Now, what I'm about to show you is going to sound very repetitive, but it's important to remember not only those characteristics, but to also see how they apply to our new family function, our new function family. So exponential function. So we have an A, B, a C, and a D. A is the vertical dilation or reflection over the x-axis. Now, the capital B value now is the horizontal dilation. However, it's not the same as this B value. This is lowercase b. This is the base of your exponential function. So let's look at this B value. So this affects the graph horizontally, is in a horizontal dilation. So it's actually going to affect the graph in the opposite ways that we see here with the vertical dilation. And when it's negative, it reflects actually over the y-axis instead of the x-axis. Next, let's look up here at the C value. Now, we're pretty accustomed to seeing the C value with x. And remember, that's your horizontal translations. Lastly, we have D, which is our vertical translation. And what I want to note is that this D value, the plus whatever the number is out here, or minus whatever the number is, it is outside or next to the base of your exponential function through addition or subtraction. Whereas the horizontal translation is inside the exponent spot with your variable x. Let's now practice using the transformational form that we just wrote down. Now, the first thing we want to look at is what is the transformation present. Now, notice my base is 2, and my variable is an x right there, but there's nothing else around it except there's a negative 1 in front. So what this means is this is an A value. So since it's negative, this is going to reflect over the x-axis. Now, to do your sketch, the easiest thing to remember is what the parent function looks like. So remember, the parent function is going to look like this. It's going to be some increasing function, and it's going to go through or have a y-intercept of 0, 1. Now, I know it's increasing its growth because my b value is 2. Now, I'm going to take this graph and I'm going to reflect over the x-axis. So the easiest way to do it is to take the y-intercept and reflect and move it down below the x-axis. Now, look at the behavior. What's going to happen this time is now it's going to be asymptotic still to the x-axis, but now look, it's pointed in that negative infinity direction. Let's look at our characteristics. The domain is still all real numbers. The parent function's domains are all real numbers, so it doesn't matter how you transform it, the domain will always be all real numbers. Now let's talk range. The range is below the x-axis. So the lowest it can be is negative infinity, and the highest it can be is 0. So that's how I'm going to write my range. Now the y-intercept we already figured out is 0, negative 1 through the reflection. In this example here, I can see that the only transformation is horizontal. So this is a C value. And if we look at what we wrote down previously, because it says x minus the number, what this tells me is my C value is positive, which means it's moving to the right. So this graph is going to move to the right 4 units. So again, I'm going to start with the parent function, which is 2 to the power of x. Now, I know this is exponential growth because, again, my base is 2, and 2 is greater than 1, so that makes this an exponential growth problem. Now let's sketch this. So like in the previous problem, we're going to take this y-intercept and use it as a guide. So we're going to take this and move it to the right 4 units. That's the only transformation. So the behavior is going to be exactly the same. It's still going to be asymptotic to the x-axis, and it's going to be increasing. So the domain again is all real numbers. Now the range, the graph didn't change its position vertically. So what we can see here is the range is still going to be 0 to positive infinity. Now there's going to be a new y-intercept, so let's calculate it. Remember, we're going to take 0 and evaluate it into our problem, or our function. In this example, we can see that, again, there's one transformation, and notice this is outside of the base and the exponent. So this tells me this is a vertical translation. And since it's negative, that means it's translated down 3 units. So my parent function is 2 to the power of x, my base is 2, and 2 is bigger than 1, so this is growth. Now I'm going to translate this down 3 units. So again, the easiest way to do this is to take the y-intercept and move it down 3 units. So I'm going to count down 3 units. So it's already up at 1. So if I do 1 minus 3, that means the y-intercept is going to be at negative 2. So again, my domain is all real numbers. Now my range is interesting. My original function, the range is 0 to positive infinity, but I've moved my graph. So by moving it vertically, I've actually moved my range. And by moving it vertically, I've moved what it's asymptotic to. So if the graph originally is asymptotic to the x-axis, then if I move it that horizontal line or that axis down 3 units, that means my graph is now asymptotic to the y value or horizontal line of negative 3. It's very similar to what we experienced with rational functions. So I now can see my range is negative 3 to positive infinity. My y-intercept I can see is 0, negative 2.